Hi folks, this is CU speaking again. What was easy, we talked about last time how to find a date on the integrated circuits. Now we talk about the real deal, what's inside these packages. Let's start it. So before we talk about the packages themselves, let's clarify some very simple things. The most common technologies used for integrated circuits are still two of them, TTL and CMOS. So for TTL, there were back in time two basic versions, the military one, and we recognize it by having the number 54. We're going to find this in examples. And commercial ones having the 74. So that's how we make the first distinction. 54 military, 74 commercial. I'm going to talk about this a bit later to the end of the video. The CMOS. There are three versions of the CMOS, or three subfamilies. The first generation, second, and third. First generation is recognized as being the 4000 series, the second generation HC, and the third generation HCT. So let's go for examples because it's much easier, but keep this in mind. Two basic families, TTL, CMOS, and for each of the TTL and CMOS, we have several subfamilies. So here we start with the TTL technology. This is a military package, not only because it's looking golden plated, it's a bit scratched, don't worry about this, it's very old, it's 54 years old, made in 1970. It's from my old collection. So, at the beginning of the code, you may have letters. Here there are no letters, but usually there are. And what these letters send you to? To the manufacturer name. Reminder, I have it here. At this moment, just keep in mind from the manufacturer names, which are right here, two of them, SN, they are used by Texas Instruments, and DM by National Semiconductor. So let's go back. Right here. SN, so this is made by Texas Instruments. It's 54 because it's the military series. And then I drew a red line here because you identify the first two digits representing the family, military or commercial. So this is 54, that one is 74, so that's commercial, it's plastic made, there's military, ceramic, golden plated. And then, what's after the 54? What's after the 54, you may have two or three digits, and they represent the actual schematic, the electronic diagram, which is inside the package. How do you know the electronic diagram? Then you have to go in a catalog, or you simply go on Wikipedia or in other places, and you're going to find out. I am very familiar with a lot of these numbers because I used them for so many years. For instance, this one is a 4-bit binary counter, 193. But this is the number telling you specifically what's inside the package, what is the diagram. And the letters coming at the end, they specify how the package is made. So it may not be a big interest for the most of us, only for the designers. For instance, J is the letter they use for ceramic package. N or P, they are used for plastic package, and so on. You may have combinations of these letters, but you don't worry much about it. So this was 54 military series, made by Texas Instruments SN. What's inside the package 193 is the code they wrote to specify the electronic schematic. Why did I cut the other line? Because it started with DM. DM are letters used by National Semiconductor, and the code they used was 7563. This is very rarely used, actually not in use at all today, and the reason it's on the package is because it was the equivalent of this one made by Texas Instruments, okay? But we are not interested about. Now, another example is here. That's a commercial package. How do I know that? Because of the number starting 74. Now the point is, at the beginning, the first subfamily they ever made was like this. There was no separation between the family number, 54, and the code of the electronic diagram. But after a while, what happened was, even for the commercial series was absolutely similar. Here is 74, which is commercial. DM is for National Semiconductor, and this is their logo. Okay? Why the code of the package is DM7407? Because I told you it has to start with one of the two codes, either 54 or 74. Here there are also numbers 9112. Yes, you can recognize it now. It doesn't matter the letters before. This is representing the manufacturing date. Can this be the manufacturing date? In the theory, yes, because it may be 1974, the week number 7. But because it's preceded by the M, which are the letters for the manufacturer, and it starts with 74, which is actually not the year, but the series, the family of the circuit, and N at the end means plastic package. This is the actual code, and this is the date. Okay, so 54, 74. After a while, the engineers realized that the consumption of these packages may go in milliamps, 20, 25, up to even 50 milliamp consumption per package, which is not much, 50 milliamps. However, when you put tens of them together in a portable package, in a portable device, in a portable equipment, then it may become important. So they were asked to do, especially for the military applications, packages consuming less. So they said, we're going to use the letter L for low consumption. And where they put that letter L? Right here as a separating letter between family number and the diagram number. Because the diagram for this one is 07. Okay? So these are just amplifier, no inverters involved, just amplifiers, 07. So they put the letter L between. But the letter L is actually what? Low consumption. So if you just want a comparison, let's take an old Toyota Tercel 87 and to take, let's say, a Mustang, a Ford Mustang. Both of them can run on the highway. Obviously, Toyota Tercel has a much lower consumption, but is a consequence to that. The speed is much lower, or if you want the acceleration, is much lower. So for that reason, even if the packages with the letter L, they consumed 10 times less energy than the regular ones, the original family with no letters between family number and diagram, that series, that subfamily did not last long because the engineers were asked, hey, do you know what? Restore some of the original speed of that. So they made something like a Volkswagen, which is not as slow as a Toyota Tercel, but not as fast as the speedy cars like Porsche or Mustang. So then the series, realizing that, was called LS. L stands for low consumption, and S, we take it from speed, but actually it's coming from the family name of the engineer who invented this. It's Walter Schottky. So S comes from Schottky, but actually we take it as from speed. They are not as speedy as the original packages, but they restore some of the speed. So this is why the two letters, low power, low consumption, and speed, Schottky circuits, these letters are between the family number and the diagram number. Okay? Later on, for some special applications, the engineer were asked, you know what? We have some special applications when I'm not interested about the consumption at all. Like somebody who's buying a Porsche or even a more consuming car. Then they said, what am I going to do? SN is the name of the manufacturer, Texas Instruments. You can even see the logo here. Is a miniature map of the Texas state. Then 74, that's a commercial package. Then 245, there are a series of drivers or amplifiers inside the package, and the letter N says is a plastic package, but the letter here in the middle, between family number and the electronic diagram, is the letter F from fast. These are fast integrated circuits. All these are part of what big family? TTL. This is fast, so I'm not interested about the consumption, just give me the fastest speed you can do. And by the way, if you talk about the speed, if you measure it in a frequency, this one can go up to 50 megahertz. LS goes to maximum 35, so it's not that far, but it's not as speedy as the original one. Okay, so then I'm going to have another example here. DM, this is National Semiconductor. Again, here is the logo. In the top is the manufacturing date, but here, DM are the letters for the manufacturer. 74 is the series, is the original series, because there are no letters here between where I drew the red line. And the package is 150. It doesn't matter, it's a kind of demultiplexer 1 to 16. And the package is plastic made because the letter is N. So this was about TTL. And one last example here, one much more modern series of packages is that one here where SN, as it happened before, Texas Instruments, 74 is commercial, but it's not LS as before, it's ALS, Advanced LS. 540 is a code for the electronic diagram inside 8 drivers in the same package. This is one of my favorite packages because inputs are on the bottom side and outputs are on the top side, and they go straight forward. Like this is the pin 1, this is the pin 10, 11, and 20 here. 19 and 1, they are designed for the control. And then input here and output here, drivers. One driver, second, third, fourth, fifth, sixth, second, and eighth. So there are 8 drivers inside, and they go just straight forward, input to output right away. Okay, so this is ALS. So I'm stopping here with the description of these subfamilies of the TTL, just retaining 2 of all of these, because the original series is very difficult to find today. LS is the most ever sold series or subfamily of the TTL, and more modern than LS is ALS, which is extremely used today too. So LS and ALS. A is for advanced, L low power, S Schottky or speed. So Speedy LS. CMOS. So for the CMOS, first of all, what does it mean? Complementary metal oxide semiconductor. You put only the first letters together, you make the acronym, you make CMOS. What metal oxide is used inside is, in the most of the cases, aluminum oxide, which is combined with silicon, and this is the semiconductor kind they make. So metal oxide, aluminum oxide, plus silicon, and you have that very special technology. Why did they invent this one? Because the consumption for the CMOS is 10 times lower than the LS. So if you want, it's 100 times less than the original TTL. This is why they've made it. How do you recognize it? There are 3 generations of the CMOS. The first generation is 4000 series. And the first thing you have to know, the power supply voltage is not 5 volts like it is for all TTL, but is between 3 to 15 volts. So it's a very large range of voltages. They were invented for 2 purposes. The 3 volts here is for portable devices, like if you can remember the famous thing made by Sony called Walkman in the 70s, because in the 70s is when this series were put on the market. And at the same time, the voltage can be up to 15, 12 volts is right there inside the range. And because of this, the first cars using digital commands for the radio and the audio magnetic cassettes were the American cars, and they were using these CMOS working at 12 volt. So here, how do you recognize? The 4000 series, it has to start with the number 4. This here, it starts with the letters CD. CD, the first is the first letter of CMOS. D is for digital circuits, CD. These are the letters for the CMOS used by National Semiconductor. We recognize the logo now. So that package is called 4011. You are not interested about the last 3 letters because they are about the package. What's the interesting though is that at the beginning there were only 4011 without the letter B. So the first version of the CMOS packages were very sensitive to the static current, static electricity, because the consumption is 100 times lower than the TTL. So anytime you're rubbing your wiring and touching the circuit, the pins, you could even damage the package before you are connecting it into electronic circuit. But when you see the letter B, they are much better protected, so they corrected that problem greatly. The letter J at the end is about ceramic package, so that's a ceramic package. It's for military purposes, by the way, because of these codes here in the bottom we're not interested about. What's interesting is what I put in a red frame, 4011. This one here, CD, is the same letters used here, so National Semiconductor. 4078 is 4000 series, and the code 78 is for a gate having 8 inputs. We're going to talk about much later. Now, the package in the bottom here is not about the same thing as before. It's about another code, and it's going to be still a CMOS circuit. What happened? What happened is this generation of engineers designing the first CMOS generation, what did they do? They said, listen, what we're going to do, we're going to go away from the first generation of the integrated circuits, the TTL, because they were working only at 5 volts. They were very limited. So we're going to design a series of circuits working between 3 to 15 volt on a very large range of voltages. But doing this way, they also gave other codes. So the code 11 in the 4000 series is not the same code as in the 74 series. As 4078 is not the same at all compared with 7478. So the engineers and technicians now had to accommodate a new set of more than 1,000 different numbers for integrated circuits. Aside from the TTL, they had to learn now the CMOS ones. The next generation of engineers are going to try to correct that problem. We have here 2 more examples. CD4034BE. The letter B just tells you this integrated circuit is the second version of the 4000 series. So we're better protected against static. 4034. 40 is from the 4000 series. 34 is actually the code representing the electronic diagram inside. This one here, this is made by Motorola. The circuits made by Motorola have a particularity. The Motorola, like back in time in the 70s, in the 80s, even the beginning of the 90s, they were thinking about themselves, oh, we're like the #1. So all the packages made by, or the vast majority of the packages made by Motorola, they start with the #1. So neglect the #1 here, and you have the code 4543. So it's still 4000 series, and the code for this is 543. So this is my favorite decoder for 7-segment displays. This was actually designed for LCD displays, but if you don't go over 10 milliamps per segment, then you can very well control LED displays. Why is my favorite? Because just by playing with the pin number 6 potential, the voltage of the pin number 6, here is the pin number 6, you can make it working as well for common anode or for common cathode displays. It's a beautiful package. So this was about the first generation CMOS. Now, another generation of engineers, they said, you know what? We're going to redesign the CMOS because the CMOS was consuming much less, that's true. But at the same time, they became, remember my old example with the Toyota Tercel 87, this was too slow. So let's recover part of the speed of the CMOS, part of the speed for that CMOS, the first generation, and come closer to the TTL. So here you have an example, 74HC04. So what happened then? Hey, 74 is the commercial name for the TTL. Here you just pick up the number 74 because the new generation of engineers, they said, we're going to go back to the code of the TTL. We use the 74 just to say commercial, not TTL, it's just commercial. H comes from high-speed CMOS, and C is the first letter of the acronym CMOS. So that package here is CMOS based. Keep in mind, it doesn't matter what TTL package you have. It is an original TTL, you'll never find the letter C in any combination inside. If you go on the site of Texas Instruments, you're going to find more than 20 different subfamilies or versions of the TTL technologies used today. More than 20 different versions. And none of them contains the letter C inside in the combination. Why? Because the letter C is reserved for CMOS. So when you see 74, which may look confusing, I told you the last time was a simple thing about the date. Now it's not that simple. It may be confusing. 74. It may not always mean TTL. If you ever see the letter C after that, it's not TTL, it's CMOS. So that's a high-speed CMOS, But the number 04, amazingly, is the same number 04 as for the TTL. 04 is for inverters. So that package contains inverters. However, the engineers designing this new series of or subfamily of circuits called HC, they didn't respect the power supply for the first generation of the CMOS. They've made it 2 volts to 6 volts. Why is that? Because 2 volts is when you energize anything from a pack of 2 batteries. If you take a look here, rechargeable batteries, because it's 1.2 volt, a rechargeable element, unlike the disposable one, which is 1.5. So 2 rechargeable batteries, 1.2 or 1.24, 1.25 each, is about 2.5 volt both. So they are going to run out of energy with the time, and the voltage can go as low as reaching 2 volts, and the packages powered by these 2 batteries are still working. These ones called 74HC. And it goes up to 6 volts. Why? Because here I have a pack of 4 batteries. If you put 4 disposable batteries in a package, then you are going to get 6 volt. So from 2 volt, 2 rechargeable batteries, elements, up to 6 volt, which is representing a pack of 4 batteries disposable, and these packages can work. Okay? So 74HC04 inverters. 04 is the electronic diagram code representing inverters. HC, high-speed CMOS. 74, commercial package. The other example is here, made by Motorola, using the same subfamily. MC are the letters used by Motorola. 74 is commercial. H is high-speed CMOS, the letter C. 00, it contains NAND gates inside. We're going to talk about that later. But this is the code 00 for NAND gates. So far, so good. And finally, the 3rd generation, this is called HCT. So the first generation was the 4000 series. The 2nd generation of CMOS was HC. HCT, what happened was, a new generation of engineers, they just went back to the coding of the 74 series TTL. So all engineers and technicians already familiar with the old TTL, and this is why I'm insisting so much on the TTL series, because if you know TTL, you also know the 3rd generation of the CMOS technology. Why is that? 74 is the code for commercial. H and C, you know them already. H is for high speed, C is for CMOS, or CMOS-based technology inside. And the T letter, if you find it inside, it says not only TTL compatible, 100% TTL compatible. So the previous generation, the version number 2, having the power supply 2 to 6 volts, it can also be energized at 5 volt, because 5 volt is between 2 and 6. But it couldn't be energized, a TTL, an original, cannot be energized at 6 volt because it's going to overheat and burn out. This is why the 2nd generation is not fully compatible with TTL. It has to be energized 5 volts. But this one here is designed to be energized 5 volts, exactly like the original TTL. What do I want to say by that? Is that the electronic code 540, which is representing, as you've seen before, 8 drivers inside the package, and they are aligned like 218, 317, 416, 515, and so on. So 8 drivers, one after other. This one and the original TTN are interchangeable. So from an old equipment, equipped long time ago with TTL circuits, you won't find a replacement for the TTL. You don't worry about this anymore, because you find the CMOS package in the series HCT. It has to be the series HCT. And having the same code, the original package 74540 can be substituted by the CMOS package 74HCT 540. So they are interchangeable with the original TTL. So this is why if you know the TTL, you know the latest version of the CMOS, which is the HCT. Isn't that beautiful? So then, I just present you a couple of, let's call them anomalies, some flavors of the CMOS technologies. Take a look at this one here. That's an old Samsung circuit, KS74. It's very easy, it's commercial. HCT, you understand it perfectly. It's HCT, but not for the original series of the TTL, but for the LS. And they say inside the letters between family number here and the diagram number here, this is why I put both with the same color, family number and electronic diagram 540, they put all these letters HCT, LS. LS is from the original TTL, and what they want to say, this is 100% compatible with the TTL subfamily LS. So that's a kind of different flavor, okay? And this is made in 2006, by the way, the week number 25. And one last example here. That's another package made by Texas Instruments. You can barely see the logo. And they put the letter CD here used by RCA because RCA was the one building the first CMOS generation packages. But then they say 40, and after that they say 192. What happens here? In the code is a combination between the first CMOS generation and TTL. So if you look in the TTL and you look for 74192, this is a BCD counter. 192 is the code for the electronic diagram of a BCD counter. We're going to discuss it much later. But this time in this package is one of my favorite packages here. It's a counter used in the CMOS technology first generation. Why is one of my favorites? Because I can use it not only at 5 volts, this one, but unlike the original TTL, I can use this one at 12 volts as well. So when I build my counters at 12 volt, I'm going to use this kind of counter because it's 192, is the same code as in the TTL, but with the technology of CMOS. It's an anomaly, and this is why the last two examples here were just to show you that there are also exceptions on the market you have to understand. So far, so good. So now let's go back to the original document I started with, this one, because now we can understand a bit better differences between subfamilies of integrated circuits. There are several differences between the TTL military and commercial. It's not only because they write the letters 54 or 74. And the most important difference here is the power supply. Both of them are energized 5 volts. But for the military series, the power supply admits a kind of tolerance of plus minus 10%. What does it mean? 10% is the 10th part of 5 volt, which is 0.5. So the voltage can be as low as 4.5 volt, and plus 10% is 5 volt plus 0.5, 5.5. In other words, if you power this from batteries, the batteries can discharge up to 4.5 volts. And you can overpower, if you power this circuit from, if you element your circuit from a bench power supply, up to 5.5 volts without having a risk to overheat. Now the commercial series, the 74, does not have such a big 10% tolerance. It only has 5% tolerance. So 5% compared to 10 is half of it. So half of 0.5 volts is 0.25, a quarter of a volt. So here, the package is going to be considered working only if the voltage you power it with is between 4.75 up to 5.25 volts. Is a very narrow margin. Your power supply has to be very close to 5 volt. That's the big difference between the commercial and military. Now, the LS series is the same thing as the commercial from the power supply, as well as the H series or F. H is for high speed, F was for fast, and ALS was for advanced low power Schottky. So all the commercial circuits, 74 everywhere, they were all having as power supply 5 volt plus minus 5%, excepting this being the latest one. It was built exactly like the old military one with 10%. Okay, so this is why ALS is much more valuable than the older ones, even about the LS. One thing I want to clarify about the TTL before going to CMOS is why 5 volt? Remember, these circuits were designed somewhere in the 60s. So in the 60s, there were the very commonly used transistor radios, and the most of them were powered by a pack of 4 AA batteries. And most of the flashers for cameras back in time, and even today the professional users, they use for the flashes a 6 volt battery pack. What is the 6 volt? Is 1.5 per element times 4 in the pack is 6 volt. Now, can you make an electronic diagram working at 5 volts or 6 volts or 7.5 or 9 volts? Of course you can. Any engineer, even technicians, can modify diagrams to work at different voltages. Why it is 5 volts though? Is because back in the 60s, when these packages were put on the market, the military engineers realized very quickly this was the key for big diagrams on a very small silicon chip. This was the key to build portable miniaturized devices. And when you send your guys on the field, if you power these things from disposable batteries, you're going to carry a backpack full of these batteries. But if you only take a couple of packs like this one made of rechargeable batteries, like this one here, if I'm taking a look, it's 1.2 volts they say, because they only wanted to use one digit, actually 1.24. 1.24 each times 4 is 4.96, which is practically 5 volt. So this is the reason the TTL was designed for 5 volts, not because they couldn't work at 7.15 volts, not because they couldn't work at 9.73 volts, but they were chosen because everybody wanted this to be energized by a pack of 4 rechargeable batteries. Even if back in time, the only rechargeable batteries available were nickel-cadmium, and they were very poor in terms of energy, but it doesn't matter. They were still used back in time as rechargeable ones. So today the batteries are much better, but the reason is 5 volts is because a pack of 4 rechargeable, 1.24 times 4, it's exactly 5 volts. Okay? Next, CMOS, first generation. Is 3 volt the lowest value of the voltage, simply because when you had a pack of 2 batteries like in the Walkman, 2 AA's or 2 AA's, you are going to have 3 volt. So they could be energized starting 3 volt. And also remember, 12 volt is in the range, and 12 volt is because all the electronics in the cars were used at 12 volts without having to convert from 5 to 12 volt, which back in time it was extremely expensive. Now the second generation of the CMOS, 2 to 6 volt, they wanted to have a very large range of voltages, but they're not designed for the cars. So for the 2 volts, exactly these 2 batteries inside the pack, 1.24 volt each, 2.4 or 2.5 volt. So the batteries are going to run out. Even reaching 2 volts, they were still working. Today, yes, there are circuits being much better than the ones in the past, and I have some little packages, some packages about the famous 555 working at 0.9 volt. Imagine, 0.9 volt each. But these ones were designed, the HC series, they were designed to work from 2 volt to 6 volt. And finally, the third generation of the HCT, of the CMOS circuits, remember, H, high speed, C, first letter of the CMOS, T, 100% TTL compatible. They were designed at 5 volts, but with the same 10% tolerance as the original military series, as the ALS series, so they can be energized between 4.5 to 5.5. In other words, you can use a pack of 4 rechargeable batteries until they discharge to 4.5 volts, and the package guarantees, the manufacturer guarantees you the diagram is going to still working. Chances are, because the packages are very well designed today, they are going to still work even if the voltage goes below. It drops below 4.5 volt, but it's not guaranteed by the manufacturer. This is the value guaranteed. Okay? Then, last detail for today. These are the kind of packages everybody uses for little projects with Arduino boards. Okay? So these packages which are similar TTL or CMOS circuits. Now, what if you don't know what's inside? What if you have a package where, like this one here, you can barely see it, the code was removed. By whatever reason, it has no code on it anymore. What do you do then? How do you know what's inside the package? Even if you may take a guess, it's a TTL or it may be a CMOS. I know this is a TTL. So then the only solution you still have a solution for that. It's a little gadget like this one here. I used a much more expensive IC checker. This is called an IC checker or tester. And I used a much more expensive made by Beckman for many years. And he was not able to find out information about a series of packages like this one here. This one here, you just align it with the notch in the top. So you align it with the last pin right here in the button. You hold it. You pull the lever. And then I have an idea about what this package is. So I go and look for the code. This is a 7474, which was a D flip-flop. By my package is not this one. So I have to look for this one because I know that package is a JK flip-flop. There are two flip-flops inside. And take a look what happens when I press on test. Okay? It's analyzed. Gate 1, gate 2. So IC is good. So not only it confirms to me it's a 7476, but it says the IC is good. If I put the wrong package number here, so I'm going to pick up a wrong number, like this one, and I say test, it says IC is bad. Actually, the IC is not bad. It's just not wearing the code 7430. That's the problem. So you have to go back, if you have a good guess. So take guesses one by one until you find out what your package is. And if you test it again, gate 1, gate 2, okay, IC is good. So that's what you do in case if you have a package which is not encrypted for whatever reason, the inscription word out. Okay? So this was for today about the codes. Take a bigger coffee for the next time because we're going to start using them. Thank you very much for today. See you next Tuesday. Bye-bye.